Good morning. So today we will continue our set theory, and now you can see set identities. What does it looks like from our covered materials? Do you see any similar table from our classes? Do you remember logical identities? And
Yes.
this set identities,
Yes.
it's very similar, very resemble this set identities with logical identities. So now question is, how can we prove set identities? How can we prove that two sets are equal? For this, we have two powerful techniques. One of these is to prove that when we want to prove that set E1 equals to set E2. First technique is to prove that E sub 1 is subset of E sub 2, then prove that E sub 2 is subset of E1, and as you know very well, if we know that the one set is subset of other set, and second set is subset of first set, these sets are equal. But the question is how to prove that one set is subset of other set. To prove it, we can take from one set arbitrary element and prove that this element at the same time is element of another set. I will show it on the example. For instance, we need to prove that is equal by AC. Hopefully you remember from previous class, we denoted complement of set A. Sometimes it's also denoted by A prime, and sometimes it's denoted like this. So they are the same, and we can use it interchangeably, these denotions. Now, how can we prove that this is true? Do you remember any analog of this identity?
It's De Morgan's law.
Yes, it's analog of De Morgan's rule, and also called De Morgan rule for sets. Now, how can I prove? My goal is to prove that left side set is subset of this set, and to prove that AC, BC, it's subset of so if I will prove both, it means that these sets are equal. Now, question is how to prove that this set intersection of A and B, complement of intersection of A and B is subset of this set. For this, I will take element in this set. Pay attention, and I would like to emphasize that this element is arbitrary element from this set. So I will take X belongs this is arbitrary element from this set. And if I will prove that this element X is element of this set, what it means? It means that this set is subset of this set. Any questions so far? So hopefully you remember definition, what is this subset? And we know that the subset A is subset of B if any element from set A belongs set B. So if I will prove now that any element, arbitrary element from this set is element of the set, it means that I prove that this is subset. Okay, so let's now continue. So from the definition of complement, X belongs intersection of A and B, complement of intersection of A and B, it means that X does not belong A and B. Okay, now what it means? It means that it's not true that X belongs this set. So it means that not this case, then X belongs A and B. Okay. Do you agree so far?
So where is C?
How and why is the complement of A and B A or B?
David, say again. So
How
I need
is the complement of A and B A or B? Because A and B includes both A. Okay.
now I'm trying to prove it, David. Look, I want to prove this equality, this identity. I want to prove it. And for this, I'm taking arbitrary element from this set. And now my goal is to prove that this element belongs this set. So X belongs this set. It means that X does not belongs intersection A and B. Do you agree with this? This is just definition of complement of set. It's just definition of complement of set. So X does not belongs A and B. What it means? It means that X belongs A and B. It's not true. In other words, it means we have negation that X belongs A and B. And now I will continue. X belongs A and B. By definition, it means that X belongs A and X belongs B. X is element of B. Okay. Now, from here, you remember De Morgan's rule for logic, and you know that if we have negation of P and Q, it's the same as not P or not Q. So if I will use here this De Morgan's rule, we have not X belongs A or negation of X belongs B. Now, what it means, negation that X belongs A. It means that X does not belongs A, or X does not belongs B. Now what it means? Now it means that X does not belongs A. What it means? X belongs what? What set belongs?
Complement of A.
Complement of A, absolutely. So X belongs AC or X belongs complement of B. And it means that X belongs so X belongs AC, or this is not union, but this is or or X belongs BC. It means that X belongs AC union BC by definition. Look now very careful. If any questions, ask me, please. So, method is that I'm taking arbitrary element from this set, left-hand side, and I proved that this element is also element of this set. What I proved now? Now I proved not equality, but I proved now what I proved now. I proved that this expression is true. Now, what I need now? Now I need to prove that this second is true. So now it means that I should take arbitrary element from this set, and prove that this element also belongs this another set. However, here is easy way, and I believe you will like it. We can just change these arrows by B implication. Because all these implications, they are true. And now it's proved now that this set identity is true. These two sets, they are equal. Please look carefully. If any questions, ask. Also, we have another method to prove set identities. And I will show, I like it very much. Maybe you will like it. You can use both techniques to prove. So I will prove again this same De Morgan's law. And let's prove that A intersection B equals and this technique it's called membership proof. And what it means that we will construct like truth table, but in fact it's not truth table, but we have here two sets, and we will take arbitrary element, and if this arbitrary element is element of A, if this arbitrary element is element of A, we will write down here 1, and if this arbitrary element is not element of A or element of B, we will write down 0. So, but we should consider all combinations. So, what it means, 1, 1. It means that this is case when this arbitrary element belongs set A and at the same time belongs set B. Okay, so let's consider all combinations. Here is 1, 1, 1, 0, 0, 1, and 0, 0. Okay, and here now I will write down all possible sets, what we need. And we need to find what happens with set AB, intersection sets A and B. Then what happens with complement? Okay, now imagine that arbitrary element, this arbitrary element is element of A and element of B. This is first row. And what about intersection of sets A and B? So this element, we know element, arbitrary element X belongs A and belongs B. What it means? It means it belongs as well intersection of A and B. So I'm writing here 1. What about complement? What I should write here? This element belongs intersection of A and B. It means It's not element of complement of intersection of A and B. So I will write down here 0. Okay. Here I'm writing 0, 0, and I need one more column. A, C. So here both sets, in the both sets we have 0, row here 0. Any questions about this first row? Okay. Okay, help me what I should write here.
0.
Yes, very good, 0, because element belongs A, but does not belong B, and it does not belong intersection of A and B. And here, Salome,
1.
here is 1, very good. Here is 1, here
0.
0, because this element belongs A, and here we have 1. Okay, now what we have that this element belongs set AC, no, does not belongs AC, but belongs BC. What about union of the sets?
1.
1. 1, absolutely. So let's continue. Here we have 0, 1, 1, 0, 1. 1. Oh, sorry. Not 1 here, but 0. 0, 1, 1, 1, 1. Any questions?
No.
Is it clear?
Yeah, I think it's clear.
Okay, very good. Now we need to prove that these two sets are equal. And what we need just to compare these two columns. They are the same, they are identical columns. And it's proved that these two sets are equal. So to prove set identities, we have two powerful techniques. However, if we need to prove, for instance, that only A1, for instance, is subset of A2, not equality, but A1 is subset of A2, in this case, it's reasonable to use a first method, this method. Okay, let me continue. This is about membership table, and here is one more example. Here we proved that union of A, B minus B, this set is equal A minus B. We constructed membership table, and from this table we can conclude that these sets are equal. Okay, if we have 3 sets, in this case, to construct membership table, here we need, 8 rows, like truth tables, when we have 3 propositional statements. Okay, now you may be familiar with this. This is Cartesian product of 2 sets. And this is definition. What is the Cartesian product of 2 sets? This is set of ordered pairs. And you know what is set of ordered pairs. We mentioned it. Ordered pairs, it means that when a pair 1, 2 is not equal with 2, 1. Okay. This is very similar when we have 3 sets. And this is definition of Cartesian product for 3 sets. Now about cardinality. You know, cardinality, it's in case of finite sets, cardinality is just number of elements in this set. And if cardinality of set A equals n and cardinality of set B equals m, then cardinality of sets of Cartesian product, it's product of n and m, n times m. Okay. So now I have here also some optional topics. They are interesting. Optional, I mean that I will not include it in quizzes in the exams, but you may find it interesting. And here is about infinite sets. And these two mathematicians, George Cantor and David Hilbert, they study infinity and set theory, infinite set theory, and to understand how hard is concept of infinity, David Hilbert introduced infinite hotel paradox. Here is link for this video, and you can watch. I will upload this presentation on Canvas. And when we have finite sets, two finite sets, there is 2 ways to identify in which set we have more elements. One way, for example, we want to find out in the room students are more or chairs. We have 2 ways. We can count students and we can count chairs and then compare these numbers. And also there is another way. We can establish one-to-one correspondence. We can ask students to sit in the chairs, and this is to establish correspondence between students and chairs. And if there will be extra students, it means that number of students is greater than number of chairs. When we have infinite sets, only way to determine cardinality of which set is greater, only way is to establish one-to-one correspondence. And if we think if we will try to decide natural numbers are more or even numbers, and from one glass it's obvious that natural numbers are more, because even numbers, they are subsets of natural numbers. But if we will try to establish one-to-one correspondence, and if we will correspond For example, number 1, 2, 2, 4, and so on, it will be obvious that we can establish one-to-one correspondence, and it means that cardinality of these two sets are the same. So we can say that we have more natural numbers than even numbers. Also, by the way, rational numbers, and hopefully you remember what is rational number. Rational number is defined as a ratio, as quotient of integer and natural number. And here all rational numbers, and we can establish one-to-one correspondence with these natural numbers and with these rational numbers. And this correspondence look like this. So we can say that cardinality of rational numbers is the same as cardinality of natural numbers. Or in other words, we can't say that rational numbers are more than natural numbers. Okay. But not every infinite set is not with every infinite set we can establish one-to-one correspondence with natural numbers. If we will discuss set of all numbers from 0 to 1, all numbers, I mean rational numbers, irrational numbers, we can see, and I will upload that you can see it, that numbers between 0 and 1, by far this number is greater than natural numbers. We can establish one-to-one correspondence.
It's uncountable infinity.
Yes, uncountable infinity. And here is what is examples of countable infinities and uncountable infinities. Okay, now I would like to ask you to open, I uploaded on Canvas 2 PDF files, and I would like ask you to open these files 6.1 and 6.2 in the title. So here is, let's first 31, number 31. I will write down it now.
Where can I find the files?
On Canvas, do it. But I will write down now on my whiteboard. It's on the Canvas, module 8. Find the module 8. But I will write down it now. So here is given two sets.
Where is it on?
On the canvas, David. But you don't need, I will write down now here this example. So we have here two sets. Set A, it's 1, 2, and set B, it's 2, 3. And now question is to find power of set A and B. And let's recall what is power set. Power set, this is set of all subsets. So first of all here, we need to find what is intersection of sets A and B. And what is intersection of sets A and B?
Just 2.
This is just set with one element 2. Now I can write down this power set. So we know power set, this is set. That's why I open braces. And now in the braces, I will write down all subsets of this set. And this is set of one element. So it has two subsets. And one subset, you remember very well, this is empty set. And another set, it's 2. Okay. Now, next question here is to find. Next question here is to find PA. I think it's clear for you, PA. And what is PA? PA is set of all subsets of this set. So we have here empty set, set with one element, 1, 2, and itself. Any questions? Next question is to find subset of Cartesian product, to find power of Cartesian product. So in this case, we need first of all to find what is Cartesian product A and B. So I can write down below and I can continue here, P. And now let's write down A times B. What is A times B?
1, 2, 3. Oh, and the empty set as well.
First of all, let's find Cartesian. I will write down here first.
1 and 2. First one will be.
Okay, so let's write down Cartesian product of these two sets. This is
Oh, the Cartesian product, 2 and 6.
oh, there are no 6. There are no 6, David. Look, this is 1, 2, 1, 3, 2, 2, and 2, 3. And 2, 3. Do you agree? This is by definition of Cartesian product.
Yes.
If Cartesian product is not clear, I can, okay. For example, we have two sets. But first, let's first finish it. This our example. So this is Cartesian product of these two sets. Any question about it? About this Cartesian product? So we need here to find P 1, 2. I will just rewrite 2, 2, 2, 3. So Cartesian product, this is set of pairs. So now if we want to write down this power set, we should write down here all subsets of this set. But how many subsets we have? Cartesian product A times B, this is set of elements, of 4 elements. And here is 4 elements. And what will be number of subsets?
It's 16.
It will be 16, yes. So I should write down here 16 element. So first it's empty set, then set of 1 elements. There will be 4 elements. There will be 4 set with 1 element. Then we will take set with 2 elements, then set with 3 elements, and then set with 4 elements. So there should be 16 elements. But it seems to me it's not clear for you what is Cartesian coordinate, the Cartesian product. And let's A, B, set with 2 elements, A, B, and set B, set with 3 elements, C, D, E. And now let's write down Cartesian product. So Cartesian product, this is set. So I should open these braces. And now this is elements of this Cartesian product are pairs, ordered pair. So first pair it's AC, then AD, AE, BC, BD, and finally B. And how many elements we have here? Cardinality of Cartesian